All right, hi folks. I wanted to do some examples from section 5.3, which has to do with exponential functions. Now, an exponential function is a function that has x in the exponent instead of x being in the base. So let me give you an example. If I was to write, let's say, f of x equals x to the third, this is not an exponential function because x is in the base. We call this a polynomial function. But if I take x and move it up into the exponent, let's say, for example, I said f of x equals 4 to the x. Now, this is an exponential function. And we use this to model quantities that are either growing very quickly or decreasing very quickly. The graph of this function is going to be a graph that increases very quickly like this. Okay, so this is f of x, and this is x. And there is one point on the graph that we typically focus on. It's this point right here. And this point is going to be the point 0, 1 on these exponential functions. Because when x is 0, this function would be 4 to the 0, but any number to the exponent 0 is 1. So for these exponential functions, whenever x is 0, the y value is going to be 1. That's why this is a common point that these exponential functions go through. All right, well, one thing we'd like to do is try to solve exponential equations. And again, this is an equation where x is up in the exponent. All right, there's going to be a couple of ways to solve these, but here's one way. One thing to try is to see if you could get the bases to be the same on both sides of the equation. Because let me give you an example. Let's say I had 4 to the x equals 4 to the 5. Well, when the bases are the same like this, the only way this equation can be true if the exponents are equal. So I can kind of see by inspection that the only way this equation would be true is if x is equal to 5. So what that means is if we could get the bases to be the same, we can then set the exponents equal to one another. So let's do that. Well, I'm noticing on the right-hand side of this equation is the number 125. I'd like to try to get that to be rewritten as an expression with a base 5. Well, it turns out 125 is 5 to the exponent 3. Right? 5 times 5 times 5 is equal to 125. Now I do have the bases the same, right? On each side of the equation, the base is 5. So I can just set the exponents directly equal to one another. So I have negative x equal 3. I could divide both sides by negative 1, and it looks like x equals negative 3. Okay, so for this example, the solution is x equal negative 3. Type that in the answer box. And it makes sense. If you were to plug in x equal negative 3 back into this equation, you would see you do get a valid equation. All right, let's do another example here. So this one is going to be similar. And what I want to do is get the bases to be the same. So on the right-hand side, I'm seeing the number 64. Can I rewrite 64 using base 4? Well, yeah, 4 to the exponent 3 is 64, right? 4 times 4 is 16. 16 times 4 is 64. Well, I have the bases the same. Once I have the bases the same, I can set the exponents directly equal to each other. So this is going to be 4x plus 1 equals 3. Now, this is a simple equation I can solve for x. I'll subtract 1 from both sides. So this is going to be 4x equals 2. Divide both sides by 4. I end up with x equal 2 over 4. But I'm noticing my math lab says it wants a simplified fraction, so I'll just simplify this to be the fraction 1/2. So this problem, this answer here should be the fraction 1/2. All right, let's go to the next one. Take a look at this one. This one's a little more complicated because, again, I want to try to get the exponents equal to one another. But in this case, I've got to look for a common base that I could use. And I'm noticing on the left side, I have 16. So I know I can rewrite 16 as 4 to the exponent 2. But I can't write 128 using base 4 and still have an integer exponent. So let me try something else. Base 4 is not going to work. Maybe I can use base 2. Let's try that. Well, I know that 16 is 2 to the exponent 4. And it turns out I can also write 128 as 2 to an exponent. And if you try it out, 2 to the exponent 7 is 128. All right, so here's what I'm going to do. I'm going to make some substitutions. In place of 16, I'm going to write 2 to the exponent 4. But I also have to bring down the original exponent I had that was negative x plus 33. On the right side, 128, I'm going to replace with 2 to the exponent 7. But I also have to bring down the original exponent on the right side of the equation, which was x. All right, well, now I want to go back to some properties of exponents that I remember. There's a property that says if you have one exponent being raised to another exponent, that's where you multiply the exponents together. So I'm going to do that. I'm going to multiply 4 times negative x plus 33 on the left side. I'll leave it to the base 2 for right now. And on the right side, I'm going to multiply the 7 times the x. So that's 2 to the 7x. But now I have the bases the same, right? The bases are both 2. So now I could just set the exponents equal to each other. So it's going to be 4 times negative x plus 33 equals 7x. Now this is an equation I can solve. Let me multiply the 4 inside the parentheses. That looks like negative 4x plus, let's see, 4 times 33 is 132. And that's equal to 7x. I'm going to get the x's over to the right side, so I'm going to add 4x to both sides. So it looks like I'm left with 132 equals 11x. And now, last step, just divide both sides by 11. And it looks like I'm ending up with the solution, x equals 12. And again, if you wanted to check this answer, you could replace x with 12 and convince yourself that you end up with a valid solution. So I'm going to put 12 here, check it out. Okay. How about if we look at another question that involves exponential functions? All right, so this one is giving us the price of a car that's X years old. And it says, how much should a 2-year-old car cost? Well, X is really the age of the car. So in part A, what they're really telling us is X equals 2. So what they're asking us to calculate then is P of 2, because they want to know what's the price of a 2-year-old car. That really means X is 2. So all I have to do is plug in. So it's 22,285 times 0.87 to the x, but our x is 2. And this is a job for a calculator. And on your calculator, you should have an exponent button. And be careful, this exponent 2 only applies to this base 0.87. The exponent 2 doesn't apply to this number 22,285 in front. So if I work this out on my calculator, I'm getting the answer 16,868, because I'm noticing it says round to the nearest dollar. All right, let's go to part, so this was part A. Let's go to part B. Part B says, what about a 7-year-old car? Well, that just means evaluate P of 7. So now I'm just going to replace X with 7 and do the same calculation. I should see that the value goes down, because remember, the older a car gets, we expect its value to go down. So when I work this out on my calculator, I'm getting the answer $8,407. Again, rounding to the nearest dollar. Okay, so hope this helps you get started here in section 8.5. Section 5.3.